This is the EdExcel AS Level Maths Paper 2, covering the Mechanics section, and it's from the October 2021 series. Question number 1. At time t equals 0, a small stone is thrown vertically upwards with speed 14.7 meters per second from a point A. At time t equals t seconds, the stone passes through A, moving downwards. The stone is modelled as a particle moving freely under gravity throughout its motion. Using the model for part A, we have to find the value of t. Well, it's thrown upwards from the point A, and then when t equals t, it passes back through A. So the displacement then from A to A is equal to 0. What we also have been given is an initial velocity, 14.7 meters per second. It falls freely under gravity. We are finding the time, and if we go to the formula book, the formula we need to use is S equals ut plus a half at squared. And so, for part A, using S equals ut plus 1/2 at squared, S, the displacement, is 0, and the reason it's equal to 0 is because we are looking at the displacement from A to A, and this is equal to u, which we are told is 14.7. We multiply this by t, and then we have the particle which is moving freely under gravity. If we take upwards as positive, when it falls down, of course that would be negative. So we subtract 1/2 times 9.8 times by t squared. What we need to do is find out what t is. We have 0 equals 14.7t minus 4.9 t squared. So if we find out what t is, we can use the equation/function solver. We have a polynomial of degree 2 minus 4.9 t squared plus 14.7t plus 0 equals 0. So therefore, we can see then t is equal to 0, or t is equal to 3. Now, we know t equals 0 is the initial time, and so therefore we can conclude t is equal to 3. This is of course our only solution. Now for part B, we have to find the total distance travelled by the stone in the first 4 seconds of its motion. Let's quickly draw a graph. Here is a sketch of the motion of the particle, and what we need to find is the total distance. So one way in which we can approach this is to find the distance going up. We'll call this distance S1, and this also will equal the distance going down. Of course, the displacement then from 0 to 3 will be 0. And then we've got the distance between 3 and 4 seconds. We'll call this S2. Now, what we can do is find out what S1 is by using the SUVATs. If we go to the formula book, we can use v squared equals u squared plus 2as. You will find that here we have v equals 0. And so therefore, if we use v squared equals u squared plus 2as, we have 0 squared equals u squared, that's 14.7 squared, minus 2 times 9.8 multiplied by S1. And if we find out what S1 is, S1 that would equal 14.7 squared over 2 times 9.8. So it turns out we get 11.025 meters. And so S1, if we write down the value of that, we got 11.025 meters. And we can find out what S2 is by once again using S equals ut plus a half at squared. So if we use S equals ut plus 1/2 at squared, S2 is equal to 14.7 multiplied by the time, which is 4, minus a half times 9.8 times 4 squared. So therefore, S2 is equal to, if we calculate this, we end up with minus 19.6. So the distance is 19.6 meters. Minus 19.6 is the displacement. So the distance then is equal to 19.6 meters. And so therefore, the total distance travelled, we've got 11.025. This would be going up, and then we go back down. So we go up here, and then from here we go back down. So we add on another 11.025, and then we add on the distance of 19.6. Remember, distance is positive. So if we work all of this out, 19.6 plus 2 lots of 11.025, we get 41.65, or in other words, 41.7 meters given to 3 significant figures. Now, for part C of the question, we have to state one refinement that could be made to the model, apart from air resistance, that would make the model more realistic. One possible answer is, we could take into account the dimensions of the stone. For example, we could allow for spin. Question number 2. A particle P moves along a straight line. At time t seconds, the velocity v meters per second of p is modelled as v equals 10t minus t squared minus k, where t is greater or equal to 0 and k is a constant. For part A, we have to find the acceleration of p at time t seconds. Well, for part A, the acceleration is equal to the derivative of velocity with respect to time. And so if we differentiate the velocity with respect to time, differentiating 10t, we end up with 10. Differentiating minus t squared, we end up with minus 2t. And differentiating minus k, we end up with 0. So A is equal to 10 minus 2t meters per second. Now, for part B of the question, the particle is instantaneously at rest when t equals 6. We have to find the other value of t when p is instantaneously at rest. Instantaneously at rest, that would suggest v equals 0. So, when t is equal to 6, v is equal to 0. And if we substitute this into here, v is 0. This is equal to 10 lots of 6 minus 6 squared minus k. And if we solve for k, k is equal to 60 minus 36, which is 24. And so therefore, v is equal to 10t minus t squared minus 24. Now we have to find the other value of t when p is at rest. In other words, when v equals 0, we need to solve the quadratic equation 0 equals 10t minus t squared minus 24. And if we use our calculator to solve this quadratic, we have minus 1t squared plus 10t minus 24, from which we can see t is equal to 4, t is equal to 6. And so therefore, we have t equals 4 seconds. That's the other value of t. And now for part C of the question, we have to find the total distance travelled by p in the interval 0 to 6. Now before we do anything else, I think it will be a good idea to sketch the graph of v against t. Here is the graph of v against t. Here we have minus 24. When t equals 0, v is minus 24. Here we've got 4, and here we've got 6. T equals 4 seconds and t equals 6 seconds. The particle is instantaneously at rest, so v is equal to 0. Now, taking a look at the graph, we need to find out the total distance. Now, to find the total distance, we have the distance shown here in green, and we also have this distance shown here in turquoise. So, for us to find the distance, we'd have to integrate. Now, if we integrate between 0 and 4, we'd have a negative value. That's because we are below the t-axis. This will tell us the displacement. Now we want the distance, so we need the absolute value of that. and then integrating between 4 and 6 will give us a positive value. So, for part C then, the distance that's equal to the absolute value of the integral from 0 to 4 of 10t minus t squared minus k, which is 24. So here is the distance between 0 and 4. Of course, we take the absolute value of that, because otherwise we'd get a negative value, because integrating v tells us displacement. We will add on to this the integral from 4 to 6 of 10t minus t squared minus 24 with respect to t. Now, if we work this out, we have the absolute value of the following. Integrating 10t, we end up with 5t squared minus 1/3 t cubed minus 24t. And so we take the absolute value of this evaluated between 0 and 4. And then we add on 5t squared minus 1/3 t cubed minus 24t evaluated in between 4 and 6. So this is what we will be calculating. So the absolute value of this integral here for our upper limit, we have 5 lots of 4 squared minus 1/3 lots of 4 cubed minus 24 lots of 4. And then for our lower limit, we have 0 minus 0 minus 0. We will add on to this then. Well, we need to take the modulus of this. And then we add on to this the upper limit of this, which is 5 lots of 6 squared minus 1/3 lots of 6 cubed minus 24 lots of 6 minus 5 lots of 4 squared minus 1/3 lots of 4 cubed minus 24 lots of 4 and so 5 times by 4 squared minus 4 cubed over 3 minus 24 times by 4 is minus 1/12 over 3. So we have the modulus of minus 1/12 over 3 minus 0. And then we add on this result here. So we have this bracket 5 times by 6 squared minus 6 cubed over 3 minus 24 times 6, which is minus 36. So we add on minus 36 minus 112 over 3. So we will add to this 112 over 3, and then we will add on another 112 over 3. The reason for that is because the value of minus 112 over 3 is just 112 over 3. So we get a final value of 116 over 3, which to three significant figures, we get 38.7 meters. So this is the total distance travelled. Question number 3. A ball P of mass 2m is attached to one end of a string. The other end of the string is attached to a ball Q of mass 5m. The string passes over a fixed pulley. The system is held at rest with the balls hanging freely and the string taut. The hanging parts of the string are vertical, with P at a height of 2h above horizontal ground and with Q at a height h above the ground, as shown in figure 1. So that's what we see here. The system is released from rest. In the subsequent motion, Q does not rebound when it hits the ground and P does not hit the pulley. The balls are modelled as particles. The string is modelled as being light and inextensible. The pulley is modelled as being small and smooth. Air resistance is modelled as being negligible. Using this model for part A, we have to write down an equation of motion for P and write down an equation of motion for Q. Now, for part A, we know that the sum of the forces is equal to mass times by acceleration. Now, when the system moves, what's happening is Q moves down, and that's due to gravity. So the force going downwards is 5 mg, and opposing that, we have the tension in the string. And when Q moves downwards, P would move up. And that's due to the tension, and what's opposing it is the weight 2 mg. So when we come to use the sum of the forces equals mass times by acceleration, if we consider P, we have T minus 2 mg equals to ma. We'll call this 1. And if we consider what's going on with Q, we have 5 mg minus T. In other words, minus T plus 5 mg. This is equal to 5 ma. We'll call this equation 2. And now for part B, we have to find in terms of h only the height above the ground at which P first comes to instantaneous rest. Now, first thing we can do is find out what the acceleration is. So for part B, if we add together equation 1 and equation 2, T minus T is 0T, minus 2 mg plus 5 mg, that's 3 mg, 2 ma plus 5 ma, that's 7 ma. And so therefore, A is equal to 3g divided by 7 meters per second squared. Now, what's happening is, if we go back to the diagram, Q hits the ground and P moves a height of h upwards. And what we can do with that information is find out the speed P is travelling at when Q hits the ground. If we go to our formula book, we need to use v squared equals u squared plus 2as. So, if we were to use v squared equals u squared plus 2as, we have v squared, which is equal to 0 squared. Now the reason it's 0 squared is because the system is released from rest. And then we add on 2 lots of the acceleration, which is 3g over 7 multiplied by s, which is h. When Q hits the ground, P moves a distance h. So when Q hits the ground, P travels a distance of h, which is where this h comes from. So what we can now do is find out what v is. And so therefore, v equals 6g over 7 square rooted, and what this represents is, it represents the speed of P when Q hits the ground. Now, what we are looking for is the height above the ground at which P comes to instantaneous rest. So for us to find out what that is, what we can do is find out the height it's travelled. So the way we can do this then, we can recognise above the ground it starts off with height 2h. It then has a height of h which it travels, and this height is due to what we said here, the distance P travels when h hits the ground. And then after this we have extra height as well. We'll call this height capital H, and at this point over here, somewhere over here, P comes to instantaneous rest. So we can find out what H is. So again, if we use v squared equals u squared plus 2as, it comes to instantaneous rest. So we have over here, if I just rub this out and change this color, it comes to instantaneous rest when the final velocity is 0. So we've got 0 squared, and it starts travelling with a speed of what we just worked out here. When Q hits the ground, it moves with the speed of 6g over 7. So therefore, we've got 6g over 7 square rooted squared, and then we've got gravity opposing it, so we've got minus 2g multiplied by this height, h. And if we find out what h is, h then is equal to, well, here we have 6g over 7 divided by 2, so that's going to be 3h over 7. So we have 3h over 7 meters. And so therefore, we can conclude the total height is 2h plus this h, which we got from here, plus this h. So we've got 3h plus 3h over 7, which is 24h over 7 meters. And then, for part C, we have to state one limitation of modelling the balls as particles that could affect your answer to part B. Well, of course, the distance that Q falls to the ground may exactly not be h, so that's a limitation. And then for part D, in reality the string will not be inextensible. We have to state how this would affect the accelerations of the particles. So the acceleration of the balls would not have equal magnitude.